All right, so here we are. Let's look at the steady state expression from the charge control model. Okay, again, charge control model is a differential expression for the charge that's stored on the diode as the minority carriers in the diode. Okay, so we just discussed that the minority carrier distribution, say on the p side, the electrons on the p side, the minority carriers on the p side, maybe are distributed like this. And if there is a recombination in the structure, you have an electron that eventually recombines with some hole that comes on the valence band side. So the electrons that are being injected here are ultimately still converted into holes, and that is how you have electron flowing. Okay, if you don't have a recombination, the distribution looks slightly different. We've calculated that also multiple times now. You have a linear drop where really all the carriers through various scattering events make it out on the other side of the device to the metal contact that sets the excess electron density back to 0, and they make it out that way. Okay? So in either one of those processes, with or without recombination, what's critical is to know the electron density that is being injected here at the junction site in this model. Okay, so let's figure out how long it takes for these electrons to make it out of the system. Okay, we're going to go after the diffusion time this time. Okay, so let's consider the case where we don't have recombination, just for argument's sake, okay? And so that means we can kill this term in the charge control model, okay? And we know then that the difference current is the charge available at time t plus, just when we switched, minus the charge that is available at the time of infinity. That's the difference current of the electrons that have been supplied and that have then flown out. That is the difference current. We call that rate of decay now the diffusion time. Okay, the overall charge diffusion time. Now, at time equal infinity, we are assuming that the minority carrier charge is completely drained. So we have an expression for the diffusion charge, okay? And we know what charge is in the system at time equal 0. And we have calculated that. We've done this expression here. We can calculate the integral over that, which depends then on WP, which shows up here. And we have the overall current that has flown over here. So we can calculate all of these numbers. It's pretty straightforward. We're just literally plugging in these values here and put this and this. And we get an expression that reads like WP squared over 2dn, which has the diffusion coefficient in it. Okay, we can divide this factor into two components, into WP over a velocity, okay? And this is the diffusion velocity, if you will. That's the velocity you characterize the electrons that are diffusing throughout the device that make it from this end ultimately all the way out to this end. And only half of them travel to the right. So that's this factor here, okay? So that's the physical interpretation of this, of carriers traveling over the distance WP in a diffusion-dominated way. They don't recombine, and they have a diffusion velocity. So that's a concept we can introduce and use. And let's derive with this concept the steady-state diode current from here. Okay, we start again from the charge control model, but now we're saying we're interested in steady state. So we know how carriers flow through diffusion, through the system, and we're substituting in this expression the minority carrier lifetime by the diffusion lifetime. Okay? Again, we assume no recombination. All right, so let's plug this in. That means at steady state, the diffusion current is the total charge in the system divided by the diffusion time. All right, we have expressions for all of these items now. And voila, we come up with an expression for the diffusion current like this. Okay? We have the charge in the system. We calculated this now multiple times, right? And we have the expression we just had on the previous slide. So here we have an exponent. Okay? There's nothing really sophisticated going on here, but interestingly, this is exactly the same as what we had derived in a much longer expression for the diffusion limited current through a pn-diode. Okay, so the charge control model in its limits like this gives you an exact solution to the diffusion current of the system. So it's kind of rewarding to see, and it also shows how these elements are related to each other. These are not approximations that are standing sort of willy-nilly and you pull them in as you need, but they're all related to each other. Okay? So, let me conclude that the large signal response is of importance to digital applications. You have diodes in your phone. You use this all the time, whether you know about it or not. And the analytical solutions as a whole are virtually impossible to carry through. So you need to introduce an approximate model. That's the charge control model that lumps things together as an overall charge over a larger region. And with that, you can come up to a physical insight in the dynamics of the switching of the operation. Okay? Be careful on the boundary conditions that you apply. They may be dictated by external circuits, so you have to be cautious about it. So that really concludes our large signal discussion on PN diodes, and I'll see you in the next segment that we'll begin to look at another class of diodes, that's the Schottky diode. So I'll see you then. Thank you.